Hello and welcome to Void Electronics. In a previous video I managed to resurrect this 1937 Telefunken Torn.E.b radio. I had to restore some connections to the power connector, the power switch and the audio output jacks. I also had to fix the voltmeter, and now I got it working with all the factory components. However, the audio is really distorted and I noticed that one of the bands are not working. This means that we have some more work to do here. First of all, let me show you the test setup for testing it on every single band. So I have a signal generator right here. Its negative terminal is connected to ground and its positive terminal is not really connected to the radio. It only couples through the insulation on the wire, as you can see right here. This is more than enough to couple some signal in. And in order to hear a tone in the speaker, you have to generate an amplitude modulated signal. So I went for 1 volt peak to peak and a 1 kHz 100% modulation tone. At this point you may be wondering how to choose the frequency for each band. So what I decided to do is to choose the center frequency for every single band. So as you can see, the center frequency is around here, it's on number 50. In this case it is 749 kHz, so we can just dial that in, enable generator, and then we should be able to pick it up. And here it is. So I did the same thing for all bands and I noticed that band number 1 is not working. Let me demonstrate that. This is band number 1 and 134.1 kHz should fall right in the middle of the band. So let's set the frequency to that. 134.1 kHz, turn it on, volume, and we have nothing. Right here we should have a tone. And I don't like this sound at all. It sounds like something shorting out as I rotated the tuning capacitor. So in order to find the issue, I think you can simply test the coils with the multimeter. And that's because at DC they should look like a short circuit basically. So if I understood the schematic correctly, all these pins should be basically shorted at DC. These as well and these as well, except for number 37, which is the last one right here, because this one is connected to a coil through a capacitor, so it should look like an open circuit at DC. Let's see if that's the case here. Okay, 3 ohms. This is open, so this is already not looking good. And this is 11 ohms, so connection number 18 is open. There's something wrong in here. Let's move on. Nothing between 12 and 13, this is bad. And we have something between 11 and 13, which means that connection number 12 is open. And then we should have something between 38 and 39. And we don't, so these are both open. And number 37 should be open. And it is. So there are multiple things that are wrong here, and we can compare against something that we know it's working. For example, band number 2 right here. Let's see. So yeah, we have 2 ohms here, 26 ohms here, 5 ohms here, so I was right, this looks okay. We have 25 ohms here and 2 ohms here, so this looks okay too, and we should have something between 38 and 39. And we do, 24 ohms, and then between 39 and 37 it should be open. And it is. So this is what a good section looks like. Of course I did this for all the bands off camera and all of them are okay except for band number 1, which is the long wave band. Since everything is so modular, I think we can get away with removing them from the top like so. So I will move this into position. This gives us access to the screws, of course. The sections are numbered, so you can see here what you're working on. This is the right one. This is the section number 1 for band number 1. Okay, let's see if we can take it out. No, it doesn't move. I wonder if I should try to pry it out using a screwdriver. Yes. It has some set screws that keep it in place. Let's try to release the front part as well. And it's finally out. Or is it? Okay, it doesn't want to come out like that due to this capacitor. This is frustrating. So this is not the right way to remove it. Okay, let's carefully rotate it like this. And maybe we can get it out through the back. Through the bottom actually. And that's it. It's out finally. Let's see what we can find inside. Judging by the snap, these haven't been touched in a few decades. Has to be expected, of course. Listen to that. Oh, okay. So yeah, the outside panels are corroded, which is not a good sign. We have to look at the insides as well. So we have some coils like this one. I feel like this will be a tough repair. And that's it. This is what we have inside. 3 coils and 3 trimmer capacitors apparently. The windings are still open on these terminals, so I think we have to dig deeper and remove these covers. Let's see if we can do this. Now the construction here is really weird because I don't think any sort of wrench would fit in here, so I'm not sure how to remove the nuts. Maybe you have to undo them by hand or something like that. I'm not sure. And also, interestingly enough, this looks spring-loaded. Look at this. Maybe they did this to prevent the cover from cracking or something like that. Okay. I think the only way is to remove them like so, which is not the most professional thing to do. Okay, that failed, so I think we have to remove this entirely. So we have to unsolder these connections and also the connections to the trimmer capacitor right here, and then I think we can undo these screws and remove it. So this one is out, and here's the issue with it. Unfortunately, these wires broke right where they leave the solder joint, so this probably means that they broke due to mechanical stress. Let's see if we can solder them back. So this will be a challenge because we have to strip this insulation one way or another, and then we have to make them a little bit longer with some pieces of wire and then solder them back. Unfortunately, this failed because the wires broke off completely. But anyway, this is what the coils look like inside. So the options here would be to either rewind this, but I don't have the tools and the skill for that, or find some replacements from a donor radio, I guess. So at this point I will leave it as it is. I'm sorry for the disappointment here. I really hoped I would be able to fix it, but yeah, it is what it is. The next issue that I want to fix is this one. As I'm tuning it, it sounds like the tuning capacitor is shorting out or something like that. Let's try it with an antenna as well. So here it sounds like it's working okay. And here not so much, it sounds quiet. Now it sounds like it's arcing or something like that. Here it's definitely working. Now it doesn't work anymore. And so on. So let's test the tuning capacitor. So to test the tuning capacitor you have two options. You can either leave the radio somewhere in between the bands like so, or you can unscrew these two screws and then lift this plate up. And this plate will actually lift up the contacts that make contact to the tuning inductors which are inside the drum. So this will give you access to the capacitor basically. Otherwise you are testing the capacitor in parallel with an inductor and it will look like a dead short. So yeah, now the inductors are out and we can test the capacitor for shorts. And here's how you do that. I'm using the multimeter on continuity and I'm connected between 0.35, which is right here on the tuning capacitor, and 0.36, which is right here on this board. And just to make sure we are in between the good connections, we have to re-engage one of the bands like this. And it looks like a dead short, which means that the connections are okay, because as we are switching the inductor in, we get a dead short, so that's perfect. And now, of course, I removed power before doing this, and now we can tune it from one end to another. Let's hope it doesn't beep at all. Okay, we are at 100. Sounds okay. And all the way to 0 it sounds okay, so this one is not shorted, and we have to repeat this for all the three sections, of course. And then we also have to repeat the test between one of the capacitor legs and ground, because in this radio the ends of the capacitors, or the two terminals of the tuning capacitors, are not grounded, they are floating sort of. So if they short out to ground, that's a big issue. So I will do this off camera, of course. Okay, so this failed because I didn't find any shorts, so I'm thinking about doing something else. What I want to do is to sweep every single tune circuit and look for resonance and see if it's resonating at all and what is the resonance frequency. So to do this, I'm using Allen's method, Allen W2 to be precise, which is to use a signal generator that is synchronized to an oscilloscope. So the sync out of this generator goes to the scope on channel 2 using a BNC cable, and the channel 1 of this signal generator goes to a tune circuit using a 10K resistor. And on channel 1 on the scope we are looking at the voltage across the tuned circuit. And as you can see, we definitely see a resonance here that's happening below our minimum sweep frequency. Now this means that the radio is out of alignment, or we are adding too much capacitance with our scope probe, but we can ignore this because the circuit is definitely resonating, and we can take care of alignment later in this video. Okay, so let's tune the radio and see what happens. So as you can see, as the tuning goes up, the resonance moves up. And this tune circuit works just fine because at this point, if it were to short out, of course the signal would just disappear, but it didn't disappear at all. We have a nice resonance that moves up in frequency, which means that this section is not shorted. So you have to repeat this for all three sections. Now this method also failed in a way, and that's because all the three tuning sections work. So this is good news, but this also means that we didn't manage to find the fault so far. But I noticed something else. Look at this. Here we are at the end of the tuning range, we are at 0, and look, it also does this when we rotate this knob, and this time we are not turning the capacitor because the capacitor is all the way to the end, which means that the issue is somehow related to this axle here or to this knob. So yeah, I think we should remove it to see what's going on in here. Let's see if we can do this. Okay, so I think the axle here is touching the chassis and this creates the issue. Let's see. Let's try to short it to the chassis. See? Something's happening when we do this. Let's use an antenna here. Okay. So it sounds to me like the radio needs this axle to be grounded in order for it to work, and it's not grounded. So every once in a while the axle touches the chassis and that makes the radio work. Look. Right now we have the distinctive radio noise. When I remove the screwdriver we don't have it anymore. So we have a missing ground somewhere. And this is strange. So this is really weird. It's almost impossible to trace it with the multimeter, but the axle is connected to this module here, so I suspected that the entire module doesn't have ground, and that seems to be correct or partially correct. If I test it with the multimeter it looks like it has ground, but I think it's not good enough. So this probe is grounded and look at this. It works now, even the current consumption changes. And if I remove it, it doesn't work anymore. So we have ground on the front panel through a wire that is right here, the wire that I added when I reworked all the power connections. And this thing is supposed to be grounded through the front panel, but this is not happening for some reason. So yeah, look. This is vacuum tube stuff, so it's really tolerant, but a semiconductor piece of equipment would probably fry out for a missing ground or something like this. So yeah, don't do this with a transistor radio because you will probably blow up all the transistors. Just for your curiosity, look at this. Now we're testing between the ground here in the power connector and this module that is not grounded. We have 2 ohms or something like that, and this is probably too high for this to work. And let's test it at the input, 0.33. so yeah, and we also have a ground lug here with a really bad solder joint, so I think we can ground it here. Yes, this one looks good. Okay, and here's my connection here. I don't know how it looks on video, but it took me like 4 hours to figure this out. This was tough. Let's test it once again. And finally, let's test it again. Haha, that's it. Look. No more tapping sound, right? It doesn't sound like it's shorting out. And we have a lot more noise, which probably indicates that the radio is working. The setup here is not ideal, but yeah. It doesn't have a proper ground connection, and maybe that's what makes it really noisy. So yeah, we fixed it. And now that this is fixed, let's just check the capacitors and maybe change them. Now I really hate changing the capacitors unless I can prove that they are faulty. So let's prove that some of them are faulty actually. In order to do this we have to power up the radio, and then we need to check the bias on the grids of the tubes. And as you may already know, In most of the cases, tubes are supposed to be negatively biased. So if you look at the first grid, it should have some negative bias on it. And this radio has a really interesting way to generate a negative voltage based on the negative lead of the anode voltage. So it's doing this right here. This is the negative bias voltage that goes to all the grids almost, and it is around minus 1.6 volts. So we should see this voltage at most of the grids. So let's start with the audio tube. This should be at minus 1.6, right? Well, it looks like it's positively biased at around 830 millivolts, so this is definitely not right. Now we have to prove that the capacitor is at fault here. And to do this, we have to disconnect the capacitor. So let's remove the power, disconnect it, and do the same measurement again. Okay, power has now been removed, so we can safely work on this. The capacitor is out. So let's apply power once again and see what we get. Okay, this is the positive grid. Minus 1.2. So yeah, this capacitor is definitely leaky, and it matters because it has a huge voltage difference across it. So let's look at the other terminal. I guess we have the full anode voltage on the other one. Yes, 83 volts. So yeah, it has a big voltage difference across it. It became leaky, and now it's positively biasing this grid, which is not good. Okay, what about this one? This is capacitor number 76. It was basically on the anode voltage. It's really bulged up, and it's supposed to be 500 nanofarads, so let's give it a try. First of all, let's short it out to make sure it doesn't kill the meter. Okay, it's out of circuit, of course, and it's 2.9 microfarads instead of 500 nano. So this is really weird. Usually when this happens, the capacitor is leaky. So to prove that, I think it would be really interesting to see what sort of current flows into it when we turn the radio on. So let's give it a try. We have to reconfigure the meter to measure current, milliamps, I hope. Okay. And I removed the ground connection from the capacitor, so we can ground it to through the ammeter to see what sort of current we get. We have ground here on the voltmeter, and yeah, let's fire it up and see what happens. I bet it's leaky. Okay, actually it's not that bad, but still leaky. It's like 150 microamps of leakage. 120 microamps at 90 volts. Okay, not ideal, but yeah, I think this counts as leaky anyway. So what about this brown style capacitor? This is some sort of film capacitor. I'm not sure if it's paper or something else. I don't know. Let's see. This is supposed to be 0.1 microfarads, and it reads 260 nanofarads or something like that, so it's more than twice its value. Once again, let's check what sort of current goes into it when we turn the radio on. This also has a large voltage across it, so let's see. Positive probe goes here. Negative probe goes into the capacitor. We have to switch this to milliamps, and now we have to measure the current. Let's give it a try. Just 25 microamps, so it's not as bad as the other one, but it's still bad. And it's also out of spec because the capacitance is crazy high. What about the small orange ones? This one is supposed to be 100 picofarads, and it reads around 160, but we cannot rely on the meter for such low values because it reads a similar value even with the probes disconnected, so I would say this measurement is invalid anyway. Let's check the leakage. This one also has a high voltage across it, so we will go once again to milliamps. Okay, and once again let's turn on the anode voltage, and we have basically zero leakage. It's reading a small negative value, but I think this is supposed to read positive, so I'm not sure what this is. Maybe some noise or just an offset from the meter. So yeah, I would say that the orange ones are okay, but the other ones probably need to be changed. And just to be sure, let's run a small experiment here. I replaced the cap with this polypropylene one. This is not 100 nanofarads because I couldn't find any. It's 470 nanofarads, but does it matter? I don't think so. Let's turn the radio on and see what sort of leakage we get. Okay, see? That's quite a difference. So it has the same voltage across it, and let's go to microamps. And I simply cannot measure the leakage across it. So this means that the leakage is below 10 nanoamps. So I don't know what the leakage is, but anyway, the old one had like 23 microamps. This one is unmeasurable, so yeah, I think this proves that all the capacitors are leaky here. The next steps here would be to order some capacitors and perform an RF alignment. But since this video is getting really long, I think it's time to wrap it up here. So if you like this video, please give it a thumbs up, and if you're interested in more content related to electronics and programming, please subscribe to this channel because there is more content like this on the way. That's it for now. Bye.